Here we go again with some more Riemann sums. This time we're looking for a midpoint Riemann sum with 4 subintervals of equal length, and we're going from 0 to 8. The first thing I think we might want to do on this one is make a little number line here to keep track of where we're headed. We're going from 0 to 8, and we are looking for 4 subintervals. Now we know, using our old routine, 8 minus 0, that's the entire interval width, and then divide by 4 subintervals, that's going to get us a width of 2 for the subintervals. So that would be 4, that would be 2, that would be 6. However, we're supposed to be doing midpoint Riemann sums, so if we were in between a 0 and a 2, if we're looking here for our base to be 2, then we're going to use a completely different x value. We're going to use 1 to go get the height. And then same thing here, we're going to go use 3, and we're going to go use 5, and we're going to go use a 7. All right, so let me say that again. If we're going to have a base of 2, and a base of 2, and a base of 2, and we're going from 0 over to 8, like we said over here, we need to basically be stopping at the 1 and the 3 and the 5 and the 7 to get our heights. So let me go find those over here. So we're going to use, let's see, 1, which goes with -2, and then we're going to go with 3, which goes with 4, and then 5 goes with -3, and then 7 goes with 4. All right. So and it's hard to see it because you can't see the zeros in between. Let me throw some extra numbers in here. There's a 0 in between -1 and 1. There's a 1 and a 2 and a 3. And there's a 4 somewhere between 3 and 5. And then between 5 and 7, there's a 6 somewhere in there. So if we were to go from 0 to 2, you would want to use the 1 in between. And then 2 to 4, you would use the 3 as the x value in between. And 4 to 6, use the 5 in between. 6 to 8, use the 7 in between. Now you don't really have to list off all of those the zeros and the 4 and the 6. You don't have to list those off. If you understand what happened over here with the 1, 3, 5, and 7, then you are good to go. All right, and just a quick reminder of what's happening graphically. It looks like you've got a function that's going down and going back up and down, but just for the sake of simplicity, I'm going to say we're on the way up. And if you're on the way up, you're looking for a height that comes from the middle of your rectangle. Okay, so as an example, if this is a 2 and this is a 4, you're looking at a 3. That's the key right there. So go find the height that's associated with that x of 3. All right, knowing that the bases are always 2, the integral is going to be a 2 times a something plus a 2 times a something plus a 2 times a something plus a 2 times a something. And it's always the y values that you're going to plug in there. Now this may feel weird to you, but we have a -2 for the first height, and then a 4 for the second height, and a -3 for the third, and a 4 for the final. And we work that all out, and we get 6. Let me double check that. This is going to be -4 plus 8 minus 6 plus 8. That's 16 minus 10, which is 6, and there it is. The answer is 6. All right, moving on. Number 8. Now we're looking for part A, left Riemann sum. Left-hand Riemann sums on the subintervals -1 to 1, 1 to 3, 3 to 7, 7 to 10. So there's 4 of them. So we're going to go -1 to 1. I think these are some of the easiest ones because they tell you exactly where to go from and to. And we're doing lefts, so that means the left side of this, you'd use the 7 for the first height. All right, and the base was 2, so we're going to say 2 times the height of 7. Plus, next up from 1 to 3, that's a base of 2, and we're using the left, so it's a base of 2, and the left height is a -2. Next up, we're done with that one. We're up to the third one. From 3 to 7 is a base of 4, so this will be a different base this time. They never said equal subintervals up here. They just said these given subintervals. Okay, so a base of 4 from 3 to 7, and then we're looking for the left side of that. Okay, and it turns out they're both a 4 in that case. So, and then 7 to 10, that'll get us a base of 3. So we'll add a base of 3 times the new height of, use the one on the left. We'll be using the 4. You don't use the right. All right, work that out. So that's what, 14 minus 4 plus 16 plus 12. Let's see, that would be 10. These first two right here, 10 plus 28 more. It's looking like 38 square units. All right, so there you go for the left rectangles. Let's go with the right hand rectangles now. So for the right hand rectangles, let me go ahead and erase the red circles here. And I think we can keep the intervals the same. That's not going to change. So let's see, -1 to 1. So for -1 to 1, oops, let me undo that, get those back in there. And we'll just get rid of that guy. So from -1 to 1, we're going to use the right hand side, so it'll be a -2. And then we'll use a 4 for the right hand side and a 4 for the right hand side. I'm just looking at each of these arcs. Right hand side, right hand side, right hand side, and right hand side. All right, and we know the bases already. So our integral is approximately equal to a base of 2 times something plus another 2 times something, and then there was a 4 times something, and then the 3 times the something. And the somethings are the -2, the 4, these are the f of x values, remember? The 4 and the 3. We're just talking about these guys right here. All right, and we just go work that out. So that's -4 plus 8 plus 16 plus 9. Let's see, that's 24. 33 minus 4 looks like 29 square units. All right, that's it for number 8. Moving right along. We got an A and a B. We're looking for a right Riemann sum with 5 subintervals of equal length. So here we go back to our total width is 9 minus -1, which is 10 over 5. So the width should be 2. And if we start at -1, you're going to go to 1 because that's 2 units away. Then you're going to go 2 more units. Add 2, you get to 3. Add 2, you get to 5. Add 2, you get to 7. Add 2, you get to 9. Now these are always going to be 2 here because they said equal subintervals, unlike the last one where it was not equal subintervals. Okay, so equal subintervals, and we're saying that our integral is approximately 2 times the first one, 2 times the second one, 2 times the third one, and 2 times the fourth one, and 2 times the last one. And then we'll circle these guys, how about in some green? We're doing right hand, so on the right side, and then on the right side, and then on the right side, and right side. So we should be starting with a -2, and then a 4, and then a -3, and a 4, and a 1. Working that out, you can do that quickly in your head probably. I'm just going to fast forward. I believe the answer is 8. Double checking, -6, -4, that's -10 plus 16 more is 6, 7, 8. Yes, that is it. All right, let's go back to the table. I'm going to erase some of this so we can do this again. We'll do it from scratch. We're going to again go from -1 to 1. That's 2 units, 2 units, 2 units, 2 units, 2 units. You're adding 2 on those x values. Start at -1, go to 9. Next, you're using the left-hand side, so the left side of this. Then it's the left side of this, and it's the left side of this, and the left side of this, and the left side of this. So you will not use the 1 this time. All right, so the integral this time, well, let's see, it's always a base of 2, right? So that's always the same. We'll throw your 2 times everything. 1, 2, 3, 4, 5. Good. It's good to show your rectangle areas before you go factoring out the 2. And let's see, we were going to use, what was that, a 7, and then a -2, and then a 4, and a -3, and a 4. And just like that, we work it out. So that's a 14 minus a 4 plus an 8 minus a 6 plus an 8. I like to do positives together. Let's see, 8 and 8 is really 16, plus 14 is 30, and then we're going to subtract 10. So we're looking at 20. There you have it. There's the answer to number 9. Moving on to number 10. We've got a different style question here. It says, the table above gives selected values for the strictly increasing function f of x on the interval -3 to 5. Kind of interesting they told us that. We may or may not need that fact. Next up, it says approximate the definite integral from -3 to 5 using a right-hand Riemann sum with 4 subintervals of equal length. Is this approximation an over or under approximation of the true integral? And justify your answer. Okay, so let's break this down a little bit. First thing, we need to find the width. Right? We need to find the width of all of these equal subintervals. So we are definitely going from the high down to the low, and you're going to break that up over 4 subintervals. That's going to be an 8 over 4, so your width is 2. Now we know how this works. You start at the -3, the low value. You go 2 units up. If you add 2, you get to -1. If you add 2, you get to 1. If you add 2, you get to 3. If you add 2, you get to 5. Now if you're ever doing one of these table problems and it doesn't land nicely on a next x value, there's an x value missing, for example, that means you've calculated your 2 wrong, or you're miscounting up here in the table. It should line up. It should work out nicely, I guess is what I'm saying. All right, since we're doing right-hand Riemann sum, we're going to do the usual. We're going to grab the one on the right. That would be this guy. And then end of this interval would be an 8. End of this interval would be the 19. End of this interval would be 34. All right, so the estimate, the integral of -3 to 5 of f of x dx can be approximated by, let's see, it's a base of 2 times a height of 1 plus a base of 2 times a height of 8 plus a base of 2 times a height of 19 plus a base of 2 times a height of 34. And we work that out. And let's see, that's going to be 2 and 16 is 18 plus 38 more plus 68 more. Working that out carefully. You can show some extra steps in there if you like, but it is 124. Okay, now they mentioned it was strictly increasing, and they wanted us to find out if this is an over or under approximation. So what I like to do on these is not draw a perfectly drawn graph, because we don't know exactly what the graph looks like, but I do want to have a strictly increasing interval. Strictly increasing function. So let me go sketch a little picture of that. So strictly increasing, and we could even go from that -3 over here, and it's on its way up. In general, I don't need to worry about all of the details about the negative x values and negative y values, but if you wanted to be more accurate, you could do that. So it could look something like this. Okay, so if that's your picture, it's definitely strictly increasing. If you were to draw right-hand Riemann sums on that, let me just jump in here anywhere. A right-hand Riemann sum, I think you can tell right there, is doing what? Over or under approximating. And you're right if you said over approximating. We got this extra area up here that we did not really want. You know, I mean, we really wanted the area under the curve, which is all down here. We want all of this green stuff down here. We didn't want the purple up top. Now, if you're wondering if it had something to do with the shape of the graph that I just drew, let me draw you another one. If you're thinking, well, maybe because it's concave up, but maybe it's increasing, but it's concave down. It does not matter. Check it out. Here's just a random right rectangle. Here's another right rectangle. It has to do with the fact that the function was strictly increasing, not concave up or concave down. Because this one over here, this was slightly concave up, and this one over here was definitely concave down. This one over here, the first graph I drew, was almost linear, but it was a little bit concave up. But, you know, if I had drawn linear, you would still see it's going to be an over approximation. So, I would write out a sentence. Since f of x is increasing, it's not about the concavity, folks. It's the increasing versus decreasing. Since f of x is increasing on that closed interval -3 to 5, oops, that's a comma, comma, our right hand Riemann sum will be an over approximation. And I just like to use their words. I don't get fancy with it. I take their words, I answer the question, and it's really the increasing. So this right here, the concave up, concave down, that really has nothing to do with it. It's the fact that it was increasing. Increasing means you're going to be overestimating or over approximating. All right. So moving on to the last one on the page, number 11, very similar. Maybe you want to pause it, try it out yourselves. All right, hopefully you got it. Let me go ahead and do it for you now, see if we agree. Left hand Riemann sum with two subintervals of equal length. Let's go find the width first. 5 minus -3 all over 2. That's going to be 8 over 2, which is 4. That's our width. So we're going to go from -3, and you're going to add 4 to that, and you'll land on a 1. Then you got one more subinterval, add 4 to the number 1, you're going to end on 5. And that makes sense. You started at -3, stopped halfway through, and you ended up at 5. Now what we're going to do is use the left hand Riemann sum. So we're going to go left for this guy and left for this guy. And this guy over here, the 34, will not be used at all. So the integral from -3 to 5, f of x dx, can be approximated by a base of 4 times a height of -2 plus another base of 4, remember they were equal subinterval lengths, times the height of 8. And that turns into 32 minus 8, which is 24. Now we still know this is the same table. If you hadn't caught that, it's the same table of information. And we still know that it's a strictly increasing function. But now this is a left-hand Riemann sum. So again, like we said before, it could be increasing and concave up. It could be increasing and concave down. It could be increasing and linear. It doesn't matter to us. When we go throwing in some left-hand Riemann sums, you're going to see under approximation. No matter what shape the graph is, if it's still strictly increasing, that's going to be an under approximation. We're looking for not just this green, we're looking for the area under the red. And it turns out there is some red that's missing. That's this right here. And it's 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 this right here. And there's always a little bit that we're missing. So that means we have an under approximation. So we write it up. Very similar to the last one. There we go. In fact, I don't know if I can easily, if I could do this, that would be amazing. If I could lasso those, that would be great. Let me see if I can do that. And I think I can copy it, maybe. I'm not sure if I know how to do this on the fly here. So let's copy that. I don't know how to copy. I was thinking clipboard, but there we go. We're going to copy that, and we're going to slide down here, and I'm going to paste it. And then we'll take that, and we'll slide it over. All right. And then we just got to change a couple of things. All right, so that was probably more work than it's worth. Let me go ahead and do a small eraser here. Since f of x is increasing on -3 to 5, our left hand Riemann sum will be an under approximation. So I'll stick those in there. Our left hand Riemann sum will be an under approximation. And there you go. We are done.